Today, the big picture, we're going to look at things called power series, which that just sounds so cool. Power series. We're going to learn what these are. Now, it's still a series, so there's still an infinite number of terms, but the difference is with what we've done before and what we're doing now. Our series before, generally speaking, if our series converged, then our series was equal to a finite value. If our series diverged, then our series was either infinite or it diverged without ever reaching a value, it bounced around, it did crazy things. But our series were related very specifically to values. Now our series are going to be related to something else. So a power series is anything in the following form. And now we're going to start at 0, by the way, and I'll explain why. This is the general form of a power series. C is a constant. And although the textbooks will tell you C can be any real number, C is most of the time going to be 0. And the rest of the time, it's probably going to be 1. Now, we're going to experiment with different values of C, but just so you know that in general, C is usually 0 or 1 in all practical situations. But again, we'll do it generically and we'll figure out, what always is true. So if I expand this, what I see is when n is 0, and from now on, power series pretty much will start at 0. My first term is A0 because this is raised to the 0th power. And then my next term is A1 x minus c, A2 x minus c quantity squared, A3 x minus c cubed, ... This goes on forever. And what we see is that I'm generating a polynomial. Okay, so a power series in this form, a power series is a polynomial, and that's actually kind of cool. So I have a polynomial of infinite degree. Now, I'm really not interested in expanding this, multiplying that out. That would be nightmarish because remember, this is going to go on forever. So we say that this particular power series, the words we use, it's expanded about C, which means that value there is really, really important. Expanded about C simply means that when I am creating my power series, and you're going to have a chance to actually build your own power series, the number C is involved in every step of the way. Okay, so we like it when C is 0 because it certainly makes the explanation of the expansion easy, but I may not have a choice. Okay, I may not have a choice. C has everything to do with my original function. Now, there's 2 ways we look at power series. I'm going to just make one up off the top of my head and say, here's a power series, let's work with it. Okay, great. It's just some infinite polynomial. It's not related to anything. It doesn't have any special meaning. But then we're going to look at very specific functions, sine x, e to the x, inverse tan x. We're going to look at very specific functions, and we are going to create power series that are equal to that function. And that's the coolest part of all. A transcendental function, a function that only gives irrational output, like a logarithm or an exponential or a sine or a cosine. We're going to look at a function that gives irrational output and equate it to a polynomial where all of the terms are rational, which is crazy. We're going to learn different ways to calculate pi or e by using power series. And it's a very powerful tool. So let's start off, because if I have a power series, well, it's only worthwhile if the power series converges. If my power series diverges, it's not useful. Okay, no series that diverges is of any use to me. So let's start off with something simple. Let's start off with the following power series. And let's say we have something of the form, how about 3 over n times x minus 4 to the nth power? Oh, I'm sorry. Sorry, let me make that. Sorry. N plus 1. There we go. Because I want to start it at 0, and really wouldn't have worked very well. So I've got some infinite polynomial. That's great. Now, is this polynomial going to converge or diverge? The correct answer is, I don't know. It depends. Depends on what? Depends on what x is. If x were a large number, this part right here is acting geometric, isn't it? Let's say x was 10. If x was 10, then this would be 6 to the nth power, which is looking geometric with a ratio of 6. Oh, that probably is going to diverge. But what if x is, 4.1? Oh, then this is a really small number raised to a power. That's probably going to converge. So I have to determine if this is convergent or divergent, but I can't determine if it's convergent or divergent in general. I have to determine if it's convergent or divergent for which specific values of x. And so the way we do this is always the same. We use a ratio test. Okay, there's no other way I can prove, or excuse me, determine convergence without a ratio test. So what we do is we take the n plus first term, that's the nth term. The n plus first term would be 3 over n plus 1 plus 1, x minus 4 to the n plus 1. Let's give myself a little room here. And we're going to take the absolute value of this, and we're going to take the limit as n approaches infinity. Now, when we were practicing using the ratio test before, I said, always use an absolute value, even though we were working with strictly positive terms. The absolute value seemed kind of redundant. It wasn't going to change things, but I wanted to get you used to it. Because from now on, you're never actually going to test another series the rest of your life that doesn't include a variable. You're never going to test a series that's just a bunch of numbers. You're going to test series that involve variables, which means these quantities can be positive or negative. In fact, they are going to alternate. Okay? If x is smaller than 4, this alternates. If x is greater than 4, it doesn't. So we don't make any assumptions. We're just going to start with this and determine what we get. So let's see. Let's work with the first part here. I'm going to have the 3's will cancel, and I'll have an n plus 1 over n plus 2. Now, what about these? I'll be left with a single x minus 4. Now, the n's can't be negative, but the x can. So I'm going to put the absolute value here. It is totally correct to put the absolute value after everything, but that's the only part that can be negative. Now, when I look at this, the limit of this guy, right? This is treated as a constant. This isn't part of the limit. The limit only involves the n. So if you'd like, you could quite literally separate these two. This is not subject to the limit because there's no n in it. And this limit right here is 1. So my final limit is x minus 4. Okay? You said my final limit is x minus 4. If I did this correctly, let's see. Yes, my final limit is x minus 4. Now, when does something converge by the ratio test? Only when this quantity is less than 1. Okay, so what I'm going to do is set up a situation, figure out when the thing is less than 1. So when I'm looking at this, I have to solve this right here. X minus 4 in absolute value is less than 1. When will that be true? Well, when negative 1 is less than x minus 4 is less than positive 1, I remove the absolute value. Now, if I add a 4 to each term, I'll get 3 is smaller than x is smaller than 5. So clearly, I'm going to be smaller than 1 in absolute value anytime x is between 3 and 5. So right now, I can say that this converges when? In the closed, or excuse me, in the open interval from 3 to 5. Now, I'm not done. I'm not done. I'm guaranteeing you it's going to converge in that open interval. But what about the endpoints of that interval? What about at 3 or at 5? That's not an obvious question. What's going to happen when x equals 3 or x equals 5? Might it converge? Now, here's what we know about a geometric series. A geometric series will only converge when the absolute value is less than 1. If the absolute value equals 1, we know the geometric series diverges. So that's why when we did a root test, if we got a limit of 1, we said the test was inconclusive, probably because a ratio test was the wrong test at that point, because that thing wasn't acting geometric in nature. This is acting geometric in nature, but this is not a geometric series because of that additional term here. That means I still potentially could converge at one of the endpoints. So what we do is we actually will test both of the endpoints. Coming up with this is relatively simple. Now we need to test the endpoints to make sure that it's either going to be including the 3 and including the 5, not including either, or including one of them. We don't know yet. So we're going to test it. I'm going to erase this here so I can get more space. And I'm going to show you how to do the test because that's actually easy. This is where we use the first half of the course or the chapter. So I'm going to test. Now I have two choices. I can test x equal positive 3 first or x equal positive 5 first. And I'm going to give you a hint. One of those values will make my series alternate. See, if I replace x with a 3, then this is negative 1 to the n. That's alternating. If I replace x with a 5, then it's just 1 to the n. That does not alternate. If you start with the non-alternating endpoint, you will save yourself some work. You don't have to, but you will save yourself some work. And here's the reason. If you start with the non-alternating endpoint and you get convergence, then the alternating one automatically converges as being absolutely convergent. And you just saved yourself half the work. If you start with the non-alternating and it diverges, now you got to test the alternating to see if you get conditional convergence. Okay, so we're going to start by testing 5. So what I'm going to do is I'm going to take the number 5 and I'm going to put it right there. And then what are we going to get? We're going to get 3 over n plus 1. And this is going to be 1 to the nth power. Well, what's 1 to the nth power? For every value of n, what's 1 to the nth?
1.
1. Yeah, I'm not going to bother writing it down. Now, look at this guy. That guy looks like kind of like a what? Kind of like a, starts with an H. You know, it's one of those
Harmonic series.
Harmonic series.
I had someone tell me a harmonica series, right? So we're going to compare. We're going to compare to the sum. Sorry, this is, let me erase this a little bit tight in here. We're going to compare to the sum 1 over n plus 1. Or excuse me, not 1 over n plus 1. We're going to compare to the sum of 1 over n. Okay, a divergent harmonic series. Remember, always state the behavior of the series you're comparing it to. Now, the limit as n goes to infinity of 3 over n plus 1 over 1 over n, so times that will be right 3n over n plus 1, and that limit is 3. Is 3 a good number or a bad number? Am I comparing 3 to 1? What am I doing with 3? Anybody? What am I doing with that value?
Isn't it 3 times that?
Yeah, it basically means that this series is acting like it's 3 times bigger than this series. That number does not have to be greater than 1, less than 1. Doesn't, just as long as it's not 0 and not infinity, I did a good job.
Yeah, it was supposed to be finite non-zero. Right?
Yeah, exactly. So this series is acting like it's 3 times bigger than this series, and this series is infinite. Oh, so what can I say? This diverges. All right. That means I am not going to converge when x is 5. Now we will test 3. Had I tested 3 first, I would have still gone back and had to test 5. So I said test the non-alternating. How do I know which one's non-alternating? Well, just put it in there. 5 is bigger than 4, so I would get 1 to a power. 3 is less than 4, that would cause a negative to a power. That's why it alternated. I'm going to go ahead and erase this because I don't need this anymore.
Professor, I have a question.
Yes.
When you did the comparison, you didn't put the n equals 0 under the sigma.
Yeah.
Does that matter? Because that would create a 1 over 0.
Yeah. So we'll do it to this.
So you can do it like that.
Remember, it never matters what's happening at the beginning. It only matters what's happening. So you say, but this is starting at 0. Okay, start this one at 1 then. Remember, removing the first term isn't going to affect. By the way, that was a really good observation. Yes, this one would have to start at 1. Now, I've got divergence at one endpoint. Now let's look at the other endpoint. X equals +3. Now what have I got? Now I've got -1 to the nth power times 3 over n plus 1. I'll write it like this. I now have an alternating series. And so now normally we would say, at this point, we would normally say, all right, well, now we start by, we must consider the non-alternating series. Why am I not even going to bother with that? Because we just did.
I already know.
Yeah, we just did the non-alternating series. So we can skip that. I don't even need to bother with that. Okay, we're going to go straight to the nth term test. Remember, if the non-alternating diverges, but I pass the nth term test, that means they're doing this and canceling each other out. So we're going to do the nth term test. The limit as n goes to infinity of 3 over n plus 1 is 0. First check mark. Secondly, again, you're looking at the non-alternating when you're doing the nth term test. 3 over, replace n with n plus 1. 3 over n plus 2 is smaller than 3 over n plus 1 for all n greater than or equal to 1. Heck, we started at 0, so I'm actually going to say for all n greater than or equal to 0. Every term is getting smaller and the terms are approaching 0. Is that a good thing? That's a great thing. We just passed the nth term test. I had a divergent series that passed the nth term test, therefore the alternating series will converge. That was what last day's lecture was. That was the entire point of last day's lecture. So we can say, excuse me, we can say that this converges, what's the word?
Absolutely.
Not
Oh,
absolutely.
conditionally.
This was,
Conditionally.
Conditionally.
by the way, if this had converged, then this would be absolute convergence. But this one diverged, so I needed this condition. That's the way you think about it. So conditionally. This is why you learned that last day, because this is going to apply to basically every problem we look at. So now I'm going to change my answer. How does my answer change? Diverged, converged.
Put a bracket, include the 3 endpoint.
Exactly. In fact, I'm going to do it in blue so we know. So that is the final answer. You like that? This is not hard. Doing the test of the endpoints is actually in general really, really, really simple. And it's probably going to involve some really simple limit comparison or something like that most of the time. It's not hard. It's just not. It's tedious. It's extra work. So now we can say, whatever this is, whatever this looks like, this infinite polynomial, as long as I use it when I turn to evaluate it, call this f of x if you want. Whenever I evaluate it, as long as I pick a number in that interval, this will be a finite value because it converges. If I pick any real number outside of this interval, then this will diverge. That's what we're saying here. I'm going to show you some cool stuff. Next day, and I hate to tell you, the next day we're going to do way cooler stuff than we're doing today. Today is intro. Next day, we're really getting into the meat and potatoes of this stuff. And we're going to see the comparisons, and how we can get other functions to look like this. But I'm going to do one really cool example of that today. So let's consider another one of these bad boys. I've got the sum n equals 0 to infinity. Let's say I've got, how about n squared over 4 to the n. And this time I'll just have x to the n. You say, well, is this the form of a power series? Yes. That's the form x minus 0 raised to the nth power. Okay. All power series must be able to be stated in the form x minus constant raised to the nth. But that constant, I told you, more often than not will be 0. It can't always be 0. As we're going to see where they come from, it's not possible for it to always be 0. It's just going to be 0 more often than any other number. So right now, this is expanded about 0. So I'd like to know, does this, where does this converge? Where does this diverge? So I start just like I did before. All right, so the n plus first term. I'm going to have an n plus 1 squared over 4 to the n plus 1, x to the n plus 1 over n squared over 4 to the n, x to the n, all in absolute value. If I do this right, this should simplify and be really, really simple. There's just nothing that this should be complicated. Okay. So I'm going to have the n squared, n plus 1 squared over n squared. What about the 4s? Is the 4, I have one more 4 here than I have here. Is the 4 going to end up on top or on bottom?
On top.
Well,
On bottom.
flip that up. Yeah, I'm going to have one more 4 on the bottom. That's important.
Oh,
Does everybody see that? Because there's one more here than there is here. So if you want, you could say I can cancel and I have a 4, and then I'm going to have one more x on top than I have on bottom. But just like before, this is a strictly positive quantity, but this is not. So I can just simply make sure the absolute value. Without that absolute value, folks, this changes everything. If I do not have an absolute value there, I will not get a finite interval. I'll have an infinite interval. There's no way around it. Without the absolute value, all your intervals would be infinite in nature, and that would be not good. Okay. So with this thing here, I want to know when is this, or let's finish it first, and then we'll figure out when is it less than 0. So I have a second degree polynomial on top. I have a second degree on the bottom. What is the limit of this part?
1.
1 over 4?
1/4.
1/4?
By the way, some of you will go and expand that to convince yourself. You don't need to expand that. You really don't. If I expand, this will be n squared plus 2n plus 1. Oh, okay, lead coefficient is 1, lead coefficient is 4. I wouldn't expand this. You say, well, why not? That was easy. What if that was to the 20th power? Don't expand it. Just look at the coefficients because they're the same degree. Will they always be the same degree? Yes. They will always be the same degree because when you replace n with n plus 1, you didn't change the degrees. Oh, so when I do this, these will have to be the same degree 100% of the time. So I just need the coefficients. So this is 1/4 absolute value of x. Now, when is that less than 1? Well, rules of inequalities. When you multiply an inequality, both sides of an inequality by the same positive quantity, we know it does not change an inequality. I can only change an inequality if I multiply by a negative. Well, we're not multiplying by a negative. We're going to multiply both sides by 4. And now I've got the absolute value of x is less than 4. Okay, therefore, x is between -4 and 4. So if I get nothing else right in this problem, if I got called away right now and I can't finish, at the very least, I know this is going to converge in this interval. Agreed? I know that. So now the only question is, what about -4 and what about +4? Okay. Is it possible it converges at either endpoint? Yes, the answer is always it is possible. I don't know. I have to actually test it. So let's start with, now, which one should I choose? The +4 or the -4?
+4?
Yeah, because the -4 is automatically alternating. So I'll try the +4. And the reason, again, is simple. If I converge for the one that doesn't alternate, it automatically converges for the one that alternates, because that convergence would be absolute. Now, most of the time, you're gonna have to end up checking both. I just like eliminating a step whenever possible. It really doesn't matter. You can check either one. I'm just saying, in the long run, the time saver would be check the one that doesn't make it alternate first. So we're going to check x equal 4, and then this will become n squared over 4 to the n, 4 to the n. Oh. That's just n squared. Huh. What do you think? Does converge or diverge?
Diverge.
Yeah, is this a P series technically? Is this a P series?
Yes.
What's the P?
-2.
Yeah, by the way, nobody's going to turn around and write this as 1 over n to the -2, but you're correct. This is a P series. Clearly, these things are going crazy, aren't they? This diverges. You can say divergent P series. This diverges actually to infinity. This one's going to get big without bound. So you're going to like this. If I replace with -4, I've got n squared over 4 to the n, -4 to the n. Can I get any cancellation here? True or false? True or false? What do you think?
True.
True. So how does that help me here? Because isn't this -1 to the n times 4 to the n then as a result? So what have I actually got? I've got -1 to the n squared. But these were growing. These are not approaching 0. So this diverges. How do I know? Because these are growing, they're not approaching 0. This thing here not only gets really big really fast, this is the other kind, the horrible bouncing one. So this particular one, that's my answer. It did not converge at either endpoint. Okay, that n squared on top is what messed everything up. Had that n squared been on the bottom, maybe we get a different story. So let's try one, maybe that looks like that one. That one being the one I just said, not the one I just did. All right, so let's try. And this time, how about, let's go with, yeah, that one's a little bit busier, a little more going on here. You tend to see a lot of exponential things, and as we're going to see later, you're going to tend to see a lot of factorials. I just haven't done any factorials yet. So I've got something that looks like this. Again, I have no idea if this converges or diverges, but I suspect if x is really large, this is probably going to diverge. And if x is really close, or if x plus 3 is really close to 0, I get the feeling it might converge, but I don't know. So we got to test it here. All right, so I've got 2 to the n plus 1 over n plus 1 squared plus 1. Okay. 5 to the n plus 1, all times x plus 3 to the n plus 1. Yikes, that's a lot of stuff. And then 2 to the n over n squared plus 1 times 5 to the, make sure I got this. Oh, I'm sorry. Sorry, put it in the wrong place. 5 to the n should go down here. And then x plus 3 to the n, and all in absolute value. Okay, well, I'm going to get cancellation here. I'm going to get cancellation here. I'm going to get cancellation here. So let's see what cancels. If it helps, you can always do this. This is 2 times 2 to the n. This is 5 times 5 to the n. So what am I?
Do you have to do the ratio test?
Yes, there is no other test that can be done. Yeah, we maybe want to do other tests, but it would be inefficient. You say, well, could I do the root test? Yeah, but the ratio.
That's what I was thinking. I was just curious. Okay.
you could do the root test, but the ratio test is going to be easier. Plus the root test, the absolute values kind of put a monkey wrench in there. It makes it a little bit more awkward.
Okay.
Doing it with that term, it's just, this, you're looking at this going, this is horrible. No, this is just polynomial. This is just polynomial. That we like that. But what about the constant? These are constants. They all cancel. That's the thing I like. They cancel. Life is good. So what am I left with? I have a 2 and I have a 5, and I have only one of these. This is going to end up on top. So here's what we've got. We've got 2. I did that correctly. Is that right? I have 1, 2 left on top. This guy's going to move up on top. I have 1, 5 left on bottom. If you want to multiply that out, that's okay. I'm not. I don't feel the need to. So is everybody cool with that? That stayed downstairs. This, moved upstairs. And then one of these. Second degree polynomial, second degree polynomial. So what's this limit right here?
2/5.
2/5. This is not subject to the limit. This could literally be factored out. Now, if I had n's over here, you can't take limits separately. You'd have to make it into 2 separate limit problems. But this is not subject to the limit because there's no n's. So this is 2/5 x plus 3. Okay. After all of that, that's just 2/5 x plus 3. And I want to know, when is this less than 0? Okay. I'm sorry, not less than 0. Sorry. It's never less than 0, right? Less than 1. Well, I got to get rid of this guy. So that would be x plus 3 less than 5/2. And that would give me negative 5/2 is less than x plus 3 is less than positive 5/2. Now, if I add a negative 3 to each term, that would be negative 11/2, negative 1/2. Okay, so if x is between negative 11/2 and negative 1/2, so I know I'm going to converge in this interval. Interesting, I'm going to converge with all negative values of x, but notice I'm also adding a 3 to each one. Now, I'm going to converge for all of those negative values, but now what? I mean, now what can I do here? Well, now when I test my endpoints, I've got to figure out which one makes it positive and which one makes it negative. So I'm going to erase this. I don't need this anymore. This was all of our work. Yes, I can get this. I hate erasing in the middle of a problem, but I need the space. So which one should we check first? Negative 11/2 or negative 1/2?
Negative 1/2.
Negative 1/2, because that will keep this positive. So x equals negative 1/2. That will give me 2 to the n squared plus 1 times 5 to the n. Now, if I put a negative 1/2, negative 1/2 plus 3 is 5/2. You notice anything? True or false?
True.
True. So this is 5 to the n over 2 to the n, and what's going to happen? All cancels. Is that a good thing? That's a great thing. That means, what am I left with? I'm left with simply this. Ooh, I'm liking this. So here's what we're going to do. We are going to compare this to what? What series should we compare it to?
1 over n
1 over
squared.
n.
1 over n squared, and the series, not the term. Some folks forget the summation part. So I'm going to compare to the sum of 1 over n squared And by the way, when you're doing this type of comparison, where you start is not relevant. It's always infinity. So what you find is most textbooks, even at this point, they're just going to write it like this. It's implied that it's infinite. You can't compare it to something that's not. But the starting point can't be 0, right? Because so if you want to do that, you just write 1. But a lot of textbooks and a lot will just say it's implied that it's infinite. Where I start doesn't affect anything. Now, a convergent P series. Now, what tests should we perform?
We got $3 in. We're not gonna get nothing. We're not gonna get exactly because each side.
Limit comparison
We can do a limit comparison.
or direct? Oh,
Somebody needs to mute themselves. A little conversation in the background. Yes, limit comparison is correct. Is there one that's actually less work?
Direct
Direct?
comparison.
I can do a direct comparison this time because that denominator is bigger. I'm going to do a direct comparison just because we don't do it often enough. Now, true or false? Is this statement true or false? That denominator is bigger. So is this true?
True.
True. Oops, we were 0. See, this is what the direct comparison is. Term by term is true. So this is your, oh, by the way, what else do I need? I do need that. Remember, you got to be bounded by 0 for that to work. So what? This converges by the direct comparison test. Yes, you could have done limit comparison test. You could have done integral test, by the way, because the antiderivative would be inverse tan. I don't want to do integral test because then I got to do an infinite limit. I got to do an improper integral. Yeah, there's too much going on. Yes, integral test would have been perfect. We've actually done this problem. If you go back in your notes, we did this problem using direct, limit, and integral test before. So I did direct comparison. Okay, great. We've just proved that it converges at this endpoint. Okay, I'll write it here. N equals -11/2. The algebra can get a little bit tricky. But what you should notice is you see the same numbers. -11/2 plus 3. That's -5/2. So if it helps, let's do what we did before and break it up, actually. -1 to the n, 5 to the n, over 2 to the n. Does everybody see what I just did? Absolutely correct. Probably a good idea because canceling would be very difficult if I don't break it up because of that -1 to the n. So now what have I got? I've got -1 to the n squared plus 1. Now what? Should I do a comparison test? Should I do something else? Can I just state an answer?
We should just do the same thing on the non-alternating.
Yes.
Doesn't it just converge absolutely?
Converges absolutely. Why?
Because the non-alternating one also converged.
We just proved the non-alternating converge. I don't actually have to do anything. I don't even have to write this out. Now, part of the reason it's not a bad idea to write it out, because every now and then, when we're putting the endpoints in, every now and then we actually make a mistake and we have a boo-boo. And that thing we looked at, maybe it didn't converge. We sometimes make mistakes when we're plugging them in. Assuming I didn't make a mistake plugging in the -1/2, and I got that particular summation 1 over n squared plus 1, and that converged, I actually don't have to do the second half. Remember, that's why I said do the non-alternating first. This converges absolutely. I never actually had to do any work. This was automatic. This is why you chose the order you did. This is all correct. I could have just said this. I'd rather just say this because I'm lazy. So does that affect our final answer now?
I'm gonna put brackets around both ends.
Brackets around both ends. What I've just shown you are all the possibilities that you could have. We did a problem where it converged at both endpoints. We did a problem where it failed at both endpoints. We did a problem where it converged at one, but not the other. Those are the only possibilities. Now, the most common one, by the way, the most common result is probably converges at one endpoint, but not the other. Okay, that's probably the most common result you'll see. If it's only going to converge at one, which one is it going to converge at? If it only can converge at one?
The negative or the alternating.
The alternating one, because it would mean that you got conditional convergence of that one because it diverged. If your alternating diverges, then your non-alternating also diverged. But if your non-alternating diverges, your alternating may converge conditionally. Oh, okay. And that's how we get only one of the endpoints converging. So that's why it'd be the alternating one. This is the reason why I suggest, I certainly don't require, I suggest you always start with the non-alternating, because if it converges, then you're done. There's nothing to check on the second half. If it diverges, which it actually will probably most of the time, then you still have to check the other one. But on that one chance where it converged, you saved yourself some work. I'd rather not do all of this every single time. And I think you agree. So this is what a power series is. It looks like this. Now, where does a power series come in? Well, I'm going to show you something. I want to look at one very particular type of power series. I'll give you a hint. It's considered the single most important power series that exists without any really close second. It's the one we're going to use the most. It's the one you use the most in differential equations. It's the one you use most in graduate level courses. It's one that looks like this. Okay. I'm going to derive this next day. Today, I'm just giving it to you and say, let's play with this for a minute. Now, remember, this is a polynomial. Agreed? Let's, for lack of a better name, I didn't know myself even. I'm sorry. I'm going to call this f of x. Okay. If I write the first few terms, what will they be? Well, 1 over 0 factorial. What's 1 over 0 factorial? Anybody? What's 1 over 0 factorial?
0? No.
1 over something is 0?
Oh,
1 over 0?
What's 0 factorial?
Oh, doesn't
Yeah.
that exist?
Or 1 is 1.
1. We forgot. Yeah. By the way, here's a way you can cheat. Okay, 0 factorial. What is 0 factorial again? What is 0 factorial again? Oh, okay. It's sort of like when people on a test are like, what's the cosine of 0 again? Well, is it radians or is it degrees? I'm like, seriously, cosine of 0, just put it in your calculator. Yeah. 0 factorial is 1. That's important to remember. The first term of a power series not only can't be 0, but it certainly can't be 1 over 0. That would be, well, that'd be crazy. All right, so I have 1 over 1 x to the 0th power, that's just 1. Then my next term is 1 over 1 factorial x to the 1st. Then my next term is 1 over 2 factorial x squared, 1 over 3 factorial x cubed. I'll just do a few. 1 over 4 factorial x to the 4th. All right, on and on and on and on and on. And then we'd say 1 over n factorial x to the n. The dot, dot, dot means continue. Okay, great. Can I simplify these? Yeah, actually I can. So this would be 1 plus x plus a half x squared plus a 6th x cubed plus 1 over 24th x to the 4th. I do one more, 1 over 120 x to the 5th plus 1 over n factorial x to the n. Okay. Okay. Why am I showing you this? Because I want you to take the derivative. The derivative? It is a polynomial. No. Okay. So what's f prime of x? Well, let's see. What's f prime of x? One thing that might make this a little bit easier is I'm going to do one more term. Let me go back to here for a moment. I'll erase this. I need to fit it in here. What if I did this? Plus 1 over n factorial x to the n plus 1 over n plus 1 factorial x to the n plus 1. Now, I want to take the derivative of all of this stuff. And by the way, we could also do an integral, but on the derivative is easier. All right, so 0, 1. What's this? 1/2 x squared. What's the derivative?
X.
X.
Just x. Okay, good.
1/2 x squared.
Okay.
One sixth
One-
x
Okay, good.
to the third.
X cubed. Okay. N over n factorial. Oh, that's a pain in the butt. N over n factorial. Can that reduce? Isn't that true?
Yeah.
So what would this be?
1 over n minus 1 factorial.
X to the n minus 1. And then the next one would be n plus 1. Okay. N plus 1 over n plus 1 factorial. Oh boy. That would be n plus 1 over n plus 1 times n factorial, would it not? Oh. And what would that be?
1 over n factorial.
It'd be 1 over n factorial x to the n. And then, okay. Okay, this is all rather exciting and interesting. And hopefully something is screaming at you from your page that you're writing on going, look at me, pay attention. You guys notice anything? You notice anything interesting about f of x and f prime of x?
They're the same.
Oh, cool.
I think it's pretty obvious that f prime of x is f of x exactly. That's why I want the one extra term so you can see, oh, well, that's kind of a head scratcher. F of x and f prime of x are the exact same function, but how does that work? Do you know of any functions that are equal to their own derivative?
E to the x.
Like as in that's the only one that exists? Yeah. So guess what? This is e to the x. Not because I said so, I just took its derivative and I got the same thing. Now, the obvious question is where the heck does it come from? How would anybody have known this? Well, that's actually the basis of next day's lecture. So you're gonna have to show up on Monday to see that part of the movie, right? That's the prequel, right? We're doing the later part. So we're doing Lord of the Rings, that's the Hobbit movie, I guess. I don't know, bad analogy. Okay, I have a power series. This is obviously a polynomial. In fact, I have rational coefficients and it's a polynomial. I can't get any more rational than that. And I'm claiming it's equal to e to the x. I'm not claiming, I just showed it is. This is equal to e to the x. I mean, you gotta admit, that's crazy, right? That's crazy. I think it's crazy. But if I look at my calculator, okay, here's where it gets really, really cool. And this is part of the big picture. Okay, hold on a second. I'm gonna go ahead and do this now. Now, this is an infinite polynomial. How do you graph an infinite polynomial? You don't. You just do the first few terms. We've talked about things like asymptotic convergence. Oh, we've talked about things approaching. Okay, what if I said, let's just consider the first few terms of this. In fact, how much is the first few terms? I don't know, maybe just to the x cubed. So what if we said, let's consider two graphs. let's consider y equals 1 plus x plus a half x squared plus a 6x cubed. Let's just consider this, and let's consider y equal e to the x. And let's consider this both on the same set of axes. So let me enter the first one. Where are we here? 1 plus x plus okay, so then if I go ahead and set my, I'm going to leave it the usual negative 10 to 10 window for now. Okay. Let's see what happens. Okay, so you see something that looks like that. Okay, great, great. That's really not that exciting. All right, 1 plus x. Okay, so I got that thing there. Now let me do the e. Let me find it on here. E raised to the x. Whoops, hold on a second. That was the wrong one. Hold on, whoops. The e is too, oh, here we go. The e is so small on my screen. E raised to the x, there we go. Okay, now I'm going to do the second one. Okay, now it's hard to see. Okay, so here's what I'm going to do. I'm going to change the window, and I'm going to make the window, instead of going negative 10 to 10, I'm going to have the window go negative 1 to 10, because the stuff on the left isn't all that exciting. And I'm going to have, let's see, if I'm going to go 10, then I need to make 10 cubed, that's 1,000. So I need to make the y go a little higher than 10, obviously. I'll make the y negative 1. Maybe I'll make the y go, I'll go 100. So now what I've just done is made the x window negative 1 to 10, and I made the y window negative 1 to 100. Now let's see what happens to our graphs. So it's mostly first quadrant graph. Okay, there's our polynomial. Right, we just graphed a third degree polynomial, folks. That's all we did. Ah, so what do you notice? They stayed together for a little while, didn't they? How long did they stay together? I don't know. Let me change my window one more time. Instead of negative 1 to 10, let me make it negative 1 to 5. And now I'm going to make my y window just negative 1 to 5. What I'm showing you is we're getting behavior. Now I've got both of them are negative 1 to 5. So there's my polynomial. And here comes my e to the x. Oh my goose. Anybody notice anything? They're really close together for a little while. Do they eventually separate? Well, of course, one's e to the x, one's a cube. How do I make them stay together longer, by the way? Anybody want to guess? How do I make them stay together longer?
Add terms.
More terms. Every time I add a term, guess what? They're going to stay together longer. I keep adding terms. They're going to stay together longer. They're going to stay together longer. They're going to stay together longer. And what I have is I can use the polynomial as an estimator of the function. So why would I do that? Because if this equals e to the x, and I have to do an integration or something, well, I'm going to show you all the ways to tweak it. What if we had e to the x squared? What if we had e to the 3x? How does that change? Well, I'm going to show you. That's next day's lecture. But we can take a power series and manipulate it and tweak it. As a result, we're going to be able to do integrals of things that cannot be integrated. We're going to take functions that have no antiderivative, and we're going to integrate them anyway. Because what we're going to do is take the function that can't be integrated, convert it to its power series, polynomial, integrate the polynomial, and then answer the question that way. It's beautiful. It's crazy. It's kind of wild, and it can be scary, and you got to keep your arms inside the vehicle while it's moving. Otherwise, bad things can happen. But this is basically where the course is going. All the manipulation and all the rules, we can do things very specifically. Transcendental functions like e to the x and sine x and cos x, we can manipulate. Okay, let me do one more simple one. Sine x.
You lied to me. You told me we were done with integration.
Oh,
I don't want to go back.
we're going to integrate polynomials. The only integration we're going to do is polynomial. I mean, if I said integrate this, well, that's not intimidating. No, integrating a function is intimidating. Integrating a polynomial, oh, that's a piece of cake. So I want you to consider the following. Let's say I have y equals the sine of x, and I have y equals, I'll start with something really simple. How about x minus a 6x cubed? Now, that's just a simple cubic function. There's nothing, I mean, that's really not even interesting, right? You're thinking it's not interesting. That somebody lied to you. It is very interesting. Okay, so let me try the sine x. If I can find it on here, where is it? There we go. Sine. All right, so I've got my sine x, and then my second one I said, let's just do x minus. Okay, I'm going to just do these. Now my window, it's a sine function. I don't need my window to go more than -1 to 1. But just in case, I'll go -2 to 2 because I got a cubic in there as well. So -2, 2. And let's do the same in both directions. Whoops. 2 to 2. And the y min will go -2. We'll go just simply -2 to 2 in both directions. Okay. So the first one's my sine wave. Okay, piece of cake. Now let's do our cubic. Oh, you see at the ends? Do you notice anything really interesting? My cubic and my sine wave for most of my graph look like they're exactly the same thing. How could that be? How could that simple cubic look like a sine wave? You got to show up on Monday to see that. Are these equal? Of course not. Are they asymptotic? For a small range of values, they are. How small the range of values? Oh, I don't know. Let me. I just went from -2 to 2. What if I simply change that from -1.5 to 1.5? You're going to like this. This is where calculus heads. It's not about equals. It's about asymptotic. It's about showing how you can replace one thing with something else and get really similar results. I just made the windows slightly smaller. It's now -1.5 to 1.5 in both directions. And now I have a sine wave and I have a cubic that the naked eye cannot see the difference. Why is that important? Suppose I had a calculator that didn't have a sine function on it. And I want the sine of 0.1. And by the way, you'd have to be in radian mode. So just for the heck of it, the sine of 0.1, well, what do I get? In radian mode, make sure I'm in radian mode. I want to do the sine of 0.1. My calculator says that's approximately 0.998334416. Okay, that's what my calculator says. Approximately. I mean, it's an infinite non-repeating decimal. Okay, what if I put a 0.1 in here? 0.1 minus 0.1 cubed over 6. My calculator says for this one that it's approximately 0.09983333. 1, 2, 3, 4, 5, 6. They don't differ until the 7th decimal place. That's why we're learning this stuff.
Does every function have a power series equivalent?
Yes, they do. Everyone does. Finding them is the whole point of next day's class. There is an actual algorithm to finding it. Now, is it practical to know the power series of everything you can think of? Yes and no. There are a few that is very practical. E to the x, sine x, cos x, inverse tan, log x. Those are pretty much the only ones that you're ever really going to do and use because they show up so often. There are, for everything that exists, there is a power series, but here's the beautiful thing. here's the beautiful thing. This is why this is so important. Once I have the power series for e to the x, then I can tell you the power series for e to any function of x instantly. Once I have the power series for sine x, then I can say sine of any function of x. I call it the tweakage. Once we establish a power series for any function, then we can change the argument and immediately have a new power series. And that's where the value of this lies, because it may be necessary to integrate something that can't be integrated. You see, you cannot integrate e raised to a functional power. You can integrate e to the x, but what about e to the x cubed or e to the 10, something crazy. But once I establish the e to the x, then I automatically will know the power series for the new one. And so integrating the impossible function is the same as integrating the polynomial that I'll be able to write. And that's where we can answer questions. That's where this is powerful on the grand scale. That's where computer algorithms are going to come in. Okay, so if you asked a computer to do a definite integral of something that couldn't be integrated, it's going to give you a numerical answer. So how did it do it? It did it as a power series. How is your calculator, when you enter the log of a number, how's your calculator doing a calculation? I mean, when I hit natural log, oh heck, let me just do e. I'm going to go e to the second power, and my calculator is going to give me a number. How's my calculator doing it? Is there some little person in there really quickly calculating things? How does my calculator take an input and immediately give me an answer? It's doing it as a power series. And
I
that's
was about to ask that.
That's why sometimes, have you ever entered something in your calculator and there was a little bit of a delay? Anybody ever have that happen? I do that all the time. You enter something and maybe you have to wait a second or two and then it gives you the answer. And there's other times you can ask something, you have to wait several seconds, it gives you an answer because it took longer. What's happening is the calculator is doing the calculation, and when I get convergence, you see when the numbers stop changing, they start changing only later, then the calculator will reveal the answer. It's really easy to ask a question that a calculator takes a little while to answer just because of the nature of the problem. It will, hopefully it doesn't give you an error message. that would be below average. All right. That's how far I wanted to get today. So let's go.